not, then maybe we can properly introduce the next section. No? Okay. Okay, for this next section, we will have like an open discussion. So the idea of the open discussion is like anyone from the attendees, from the panelists, can answer. The idea is to create this idea of discussion where anyone can ask questions and the panelists or any one of you can answer them. So for this, well, Christian already presented kind of his work. So next I will please ask Jeremy if he wants to briefly present what he's doing, what he's working right now, and yeah, or we can go directly to some questions that I have prepared.
Yeah, I can introduce myself. So sorry, I apologize for the lack of camera. My computer died 3 days ago, and I'm on a backup system that doesn't have any cameras. So I'm a postdoc at Cornell University in the lab of Thomas Cleland. I work on olfaction, learning, memory, and basically right now my main project is how do we handle the very high dimensionality of olfactory inputs and how the biological system computationally transform those inputs in something that is understandable by the brain. That's the gist of it, and then translate those computational algorithms that we derived into something that can be applicable in neuromorphic hardware.
Thanks. So let's start with the discussion. So just to be clear about it, I am not an expert in neuroscience, far from it. So probably most of my questions are going to be very general. So if any one of you want to add something about it, so please save me from this. But okay, let's start with some general questions for both of you. So I believe that neuroscience can be very useful for continual. I mean, as I mentioned before, I mean, we learn continually. There is something happening in our brains that allows us to be more continual in our ways, so more fast adaptations, dreaming, and there are so many other things that we have been inspired on that allowed us to do this. But what do you think is the main like attribute or the main discovery that we can find in neuroscience, like the neuro-inspiring thing, to be applied in continual learning? We can start with Jeremy.
That's a tough question. I think I'm going to go the other way around. And in the brain, everything is continual learning. There is no snapshot of a specific data set that is inputted at a time t and then never changed afterwards. Or you don't re-update everything when you have new data coming. In the brain, the first thing is that everything is continual since you evolve through time. So all of neuroscience that study learning, memory, all of that is relevant for continual learning. And that's a very, very big field, to say the least. That would be the first point I would make. The second thing would be, you might not think about it at first, but there's also a huge field that studies forgetting in the brain. And if you want to speak about learning, you have to speak about forgetting. Since forgetting is also, at least in the brain, it's a very active process. So learning and forgetting are two sides of the same coin. And I think sometimes it's possible that continual learning literature does forget a little bit about forgetting, no pun intended. That would be a second point I would make. So I don't know if you can say there is a specific most relevant subfield of neuroscience that is relevant for continual learning, just because the literature is huge. And yeah, as soon as you start looking at how the brains learn, then you're in a continual learning setting.
Christian, do you want to add something?
I mean, yeah, I'm just gonna. I also agree. I couldn't answer something like, okay, this discovery is going to save continual learning. I don't really. I mean, it would be very hard pressed to say something like that. But what I can say is that, for instance, one thing about the human brain is that it has this ability of and not disability, it's basically restrained by evolution, right? So we have developed specific skills, and some skills are, for instance, navigational skills, and we can reuse those navigational skills to, for instance, encode abstract information with cells that were mainly specified for other things, right? So I'm right now thinking about, for instance, all the fuzz about the hippocampal place cells and grid cells that allow you to structure abstract information in a way that allows you to do generalization and so forth, right? And it turns out that it's the idea is that, well, you might need the hippocampus to sort of understand this abstraction and structure your world in specific thing in a specific way, but the basic idea is that this information then is sort of broadcasted in the cortex, right? And this type of differentiation is really not in even, it's not even thought of in models of AI, right? So and it might be that it has a very specific function, right? So I think obviously there's a lot of things that we can use in neuroscience that could help and benefit AI models, of course, right? But I think this concept of, like, I guess the main point of my talk is exactly the concept of continual learning can not only be the concept of continual learning, right? It has to be, well, how can I generalize better, or how can I structure my environment and so forth, and maybe an emergent property of all of that is continual learning, right? So that's my I guess my 2 cents on this.
Yeah, I know it's not an easy question to answer, but I mean, I need to ask the difficult questions here, no? But Jeremy mentioned something I believe is very relevant, the idea of forgetting, and I believe forgetting in humans, at least, is really important to learning things. How do you see forgetting nowadays in continual learning? Because there are really few works that talk about the idea of forgetting and a positive thing. How do you think forgetting can affect the idea of learning new abilities, or maybe helping the idea of generalization?
Yeah, so I think, like I mentioned, that forgetting and learning are two sides of the same coin, right? So if we want to get better at learning something, sometimes we need to forget something else. Let's take an example. You go to the supermarket, you park your car. If you go to the supermarket every week, you're going to park your car somewhere different every week, right? But if you never forget where you parked your car the first time, then you will go back to that place and not find it again. So in that specific case, it's an oversimplification, but that conveys the gist of it is you need to forget where you parked your car the first time to be able to update your map of where your car is now. And we look at forgetting as a bad thing, but in that case, if you don't forget, you're not adaptable to the environment, right? So forgetting the right thing is a fundamental part of being adaptable to that specific dynamic environment.
So it's kind of the idea of this inductive bias and forgetting this inductive bias that some models have learned. Or
in a way, I guess you could say that, in the sense that your previous memories would be an indicative bias of your present state, which is then biased by your past state. In that sense, yes. And that would be a wrong bias, right?
yeah, of course. I mean, if the bias is wrong and you forget, this helps you to generalize in a way.
Yeah.
Okay.
So that begs also the question of, well, biological systems work that way. Does that mean we need artificial systems to behave in the same way? In the sense that biology is constrained by a lot of things, and sometimes among others, evolution is one thing, but energy consumption is another, right? For example. So can we design systems, artificial systems, that are better at remembering and just learn to adapt differently? That's one possible answer. The second answer is we can't, and we have to copy what biology is doing in a way that's a better approach, at least at first, because we know it's a system that works. But still, the question remains open, right? It's very hard to disentangle from biology what is relevant to a specific task performance than what is not, just because biology is complicated. And that's an understatement of the century.
Christian, do you want to add something?
No, not really. I mean, I'm not so acquainted about this. I know there's a huge literature in cognitive neuroscience about adaptive forgetting. I'm not very much acquainted with it, but to me it makes complete sense, right? I mean, you don't want to retain everything that you learn, right? Because some of those things are actually to some extent bad, right? I mean, I'm even thinking of in terms of maybe psychopathology, right? Or say something like post stress traumatic disorder or something like that, PTSD, right? So there's things that there's things that you need to unlearn and forget, and it's an adaptive process for sure. But I don't have much to say about how that links to the AI side of things, to be honest.
Quick, thanks. There are a few questions in the Q&A, but I will briefly mention something that Jeremy mentioned again. This idea of if we actually want that our AI models think as humans do. I mean, if we can let our AI models actually learn as humans learn, and if it is something that we actually want. I mean, I am in the opinion that I don't know if we want that. I don't know if, as Jeremy mentioned, biology is difficult. And maybe it's too difficult to actually put all that information in one AI model. And maybe we can find another way of these AI models to learn new things and learn continually. So the question is, or the comment is, how far are we from actually understanding biology? And if this at the end is going to help us or not help us to achieve this kind of continual learner agent in the ideal world. Or if we just want an AI model that doesn't actually need the neural-inspired thing.
So, okay, so there's two things there, right? So, so the first thing is that maybe we don't want that for many reasons. Like humans are selfish, they're biased, they forget, they hallucinate, right? So they do tons of, there's tons of emergent behavior associated to the way that our brain works that are probably not wanted in the perspective of the AI, right? So that's one thing. So regarding to how far we are to really understanding, there's I think still a quite a big leap that we need to do to really understand many of the things that humans do, and specifically what are the brain dynamics and the underlying mechanism that give rise to intelligent behavior in humans, right? So we've done quite a lot of advances through the development of maybe data-driven science and also advanced methodological tool. Like I'm thinking about, in my opinion, there's always been like a before and an after optogenetics tools, before and an after fMRI, right? So this type of things. But for instance, there's this paper which used to say like, well, we have all these tools in neuroscience, but and there's this paper that came out like a few years back, which used to be called, well, it's called actually, could a neuroscientist understand a microprocessor, right? So a microprocessor is much more simple than the brain, and it turns out that, okay, there's a huge debate around that paper, but it turns out that maybe the tools that we have in neuroscience are not going to allow us to understand very, very complex systems such as the brain, right? So I think there's an importance in theory, of course, right? That's going to constrain what are the things that we're looking for and so forth. But obviously this has to be in like a constant talk with novel methods that allow to test those theories as well. Right? So I think there's still just a huge leap to understand really what the brain is doing. But there's, in my opinion, some very good advances lately.
Yeah, to piggyback on that, do we understand everything about the brain? Absolutely not. I agree with that. Did we make progress in the last 70 years? Yeah, definitely. And the tools are definitely something that helps us move forward. Now, are the tools perfect? Definitely not. Are the next tools going to be better than the one we have? Probably. It's hard to know what remains to be known when we don't know anything past what we already know. So understanding the brain might not be the only thing that we need to make progress on to develop better AI systems, but at the moment, it's also the only system that we know that does work, that is us, right? That is as intelligent, as adaptable as us. It's the only system that we know works in that way. And so we know where to go from where we are to there. We just don't know the path, but we know the end. So like we previously said, it's very hard to disentangle what's useful and what's not, what's byproduct of evolution and energy constraints and things like that. But with enough time and resources, we've already made progress. So why not make more?
Can I comment something on top of that? Yeah. So I one thing that I think should be relevant here as well is that, so in the continual learning, sort of word, there's a learning part, right? And models, they use backpropagation, and we know that the brain doesn't necessarily have a similar learning rule, right? And obviously the way that you're going to learn is going to constrain the type of representations that you're going to unfold. This is why neural networks are so, data hungry, so to speak. And that's why humans are much better at learning and at generalizing information, and probably the way that the human brain solves specific tasks is very different than what AI systems are doing. And so what's interesting here is like, well, what sort of representation does the brain sort of give rise to when it solves a task that could be useful to sort of mimic in AI systems, right? So when I was talking about this, and Julio, because we've been trying to do it, but when I was talking about this, useful abstraction of neural geometries that can help generalize and stuff like that, well, you can use that to force neural networks to behave in the same way, right? We've tried, we failed miserably, but I think it's it's not a sort of, you know, a doomed path, right? So there's things that we can understand about how the brain you know, interprets and represents specific, you know, task relevant variables, and we can use that information in AI models that could, in my opinion, I mean, the goal that we were trying to do is to speed learning and increase generalization, right? But I think there's a lot of things that can be used specifically coming from neurophysiology work and this theoretical work about, you know, trying to understand what type of neural representations are good for higher order cognition, or in this case generalization, right? That can be used to, for instance, constrain how the neural networks learn, right? So this is, I think, a very important, and I think that's where really we should sort of link, right, in between AI and neuroscience. Right? It's not so much about so much about the learning part, because it's really it's not so it's quite hard to understand how the brain really represents all of these things that it represents, right? We know what we're using in AI. We're using backpropagation, and that's it, right? So that's pretty easy in that sense, right? But how the brain does it, it's a bit more of a complex task. But we can have access to the type of representation this learning leads to, right? And so maybe, you know, trying to apply that or align neural networks to this type of representation can be like a viable solution.
I think I'm going to put a caveat on that, in the sense that because you know where you're going, basically the endpoint of your training, and if you take 1,000 different neural networks that are differently initialized, and you give them the possibility to learn, to go toward that state, the representation state, right? Then you're going to end up with 1,000 different networks that don't exactly have the same weight, for example. And it doesn't mean that in an evolving environment, when that representation needs to change to adapt to the environment, it doesn't mean that all of your 1,000 different networks are going to adapt in the same way and be adaptable to that new environment, right? You have the same thing in neuroscience, which is called degeneracy. If people want to look it up, it stems from a lot from the work of Eve Marder. Basically, she showed that you can have a lot of different networks that have the same representations, but the internal functioning is completely different. Namely, the parameters are completely different, but they end up in the same state. But that's at a specific time point. And if the representation needs to change because the environment changes, it doesn't mean all of those networks are going to adapt in the same way. That'd be the first caveat I would make. But other than that, I agree. The second thing that you mentioned is learning rules. So backprop is the basically only kind of learning rule we have in deep nets that works really, really, really well. We have others that people are trying to come up with biologically constrained or biologically plausible rules. For now, I don't think I've seen one that works as well or that is as computationally efficient as backprop. Now, the brain, we know that there's a lot of things involved in learning and a lot of rules that are involved in learning. So let's say instead of one rule in artificial networks, you have 10 different rules in the brain. Well, it doesn't mean that all the brain structure use all 10 rules. Sometimes you can have brain structure that use a couple only, or 3 or 4, and it's not the same 4 than another structure uses. That could stem from a lot of different variations between brain structure, between specific neurons, between how they're connected. There's a lot of heterogeneity in the brain. There's very little that is, I would say, standard, and drawing boundaries is very hard. So once again, disentangling what does what is very hard, just because from an evolutionary point of view, those learning rules probably stack on top of each other.
And Sorry, Christian, do you want to say something?
No, I completely agree with everything that has been said. I'm pretty fond of Eve Marder's work.
Yeah, it's great work. It's very interesting.
So in the direction that Jeremy mentioned, there is a question here in the chat. Let me read there for you. So is there any work relating to differentiating learning or forgetting rates depending upon the cost of making mistakes in different scenarios?
Isn't work relating to differentiating learning? Okay, I would not put it in those terms in terms of neuroscience work. But the idea, I would say, to answer that question is you are going to find different learning rate or forgetting rate depending upon the tasks that you ask the animal, the human to do. So if I take an example, in rat, you can do fear conditioning, where you pair a small electric shock with some signal. It could be like a ring bell or anything else. And those usually are learned extremely rapidly and very hard to forget. And you can, on the other hand, have tasks that will take monkeys months to learn because they're very hard to learn for them, just because it's so out of their normal range of behavior. So yes, although the sentence is probably not phrased the right way from a neuroscience perspective. But if you want to look at what I just talked about, you can find resources in, and it's classical tasks that are used in behavior. You'll find a lot of resources there.
Right, and if I can add, actually, so during my talk, I was speaking about adaptive learning, right? So what these tasks show is that basically when you have this, sort of context switches or these switches in state action contingencies, right? What humans actually, like if you analyze the behavior of human, what happens is that you have a very high learning rate at the moment of these change points, and as the context stabilizes, the learning rate falls down, right? So you have these adaptive learning rates. So the learning rates are actually dynamical, right? And I think that's quite interesting from a normative perspective, right? So if I now understand that I'm in a novel context, I want a high learning rate because I want to learn more from like small amount of examples. But then I need to lower that learning rate once I have, like, to some extent found more or less what the task is, in order to stabilize the learning as well, right? So these notions of adaptive learning rates, normatively speaking, are very useful, right? So and the model we developed, this neurocomputational model, is sort of the first of its kind to present this idea of how a neural network could implement these type of adaptive learning rates in this type of change point tasks and reversal learning tasks and whatnot. So although we don't have really a parameter that controls how dynamical a learning rate is, it just emerges from the neural network, right? So that's quite interesting as well. There's, from these cortical basal ganglia loops, you can make an adaptive learning rate emerge, right? So from the perspective of humans, it's actually quite interesting to have adaptive learning rates, right? And actually, even from the perspective of continual learning, right? So if I'm switching to another task, I want a very high learning rate at the beginning, and then I want it to gradually decrease, right? It makes sense.
In those sense, who or what does the information of changing this? Because I have seen some works in neuroscience. Actually, you, Christian, mentioned one, the work from Ali, that proposed using an external, that in this case is the C function, the C vector, is an external like gating function or gating vector that represent and help us change the representation in a way, no, that we have in our brain. Where does in neuroscience, where does this external representation or external vector came from?
Maybe I can have a go at that question. So that's a very good question, actually, right? So we don't really know where it comes from. It's the idea is that, so the brain is sort of wired in this, you know, hierarchical schemes of basal, like cortical basal ganglia loops, right? So if I'm performing a task, I have these different loops that are being controlled sort of in a hierarchical way, right? So you might think like, well, I understand that I am in a novel task, so I have a change in task representation, and task representation might change a new state action contingencies, right? And so these are this sort of information is going to be sort of, you know, how can I put it? Sort of passed on by the basal ganglia, and these novel projections, so these projections, these thalamocortical projections, are going to induce these changes in states, right? So where they come from, it's sort of like they come from, you know, top-down processes, but then you can go to reduce it like, where do the top-down processes come from? But the basic idea is that this is sort of controlled through thalamocortical gatings, right?
Jeremy, I don't know if you want to add something, or I can go to the next question.
Yeah, I think I'm just going to add that there's a lot of work that's been done in neuromodulators and how they can change how an existing system in the brain basically transmit information kind of work. And those neuromodulators, like they innovate the whole brain, and they are very relevant in a lot of different tasks. So if you want to look at it, it's like, so you have serotonergic system, noradrenergic system, all of those from a cellular point of view, they are extremely important to encode like things like novelty, familiarity, things like that. Yeah, I'm not an expert on those, so I'm going to stop there. But yeah.
Thanks. So next we have another question for Marty. So related to the comment about backpropagation, are there folks in continual learning applying more biological, realistic models of neurons or hidden units? I don't know if you guys know some work on continual learning, or maybe like neuro-inspired situation, applying those more biological, realistic.
I'm just, so my answer is super short. I don't know. No, to my knowledge, I don't know. I've never seen, maybe maybe some other people know actually, but like for instance, deep spiking networks that actually are implemented in continual learning paradigms. I have no clue, to be honest.
So I would not limit that to continual learning, since those paradigm or those type of algorithms, they're used, or they develop usually in context of neuroscience, and the data that is used in neuroscience is inherently temporal. So usually you won't find like the term continual learning specifically associated with those algorithms. But there are quite a few people since the emergence of backpropagation as a really good algorithm for error propagation, that are looking into how the brain can do something similar to backpropagation with its own constraints. You can look up Conrad Cording at UPenn, or also Black Richards, I think he's at Miller. They've been working on an algorithm that would potentially sustain propagation of error through deep spiking nets. You have a lot of others that are looking at those kinds of rules. But like I said, usually it's not associated with the term specifically continual learning.
Yeah, say if I may add, so these are based basically on eligibility traces, right? So yeah, there's also the work of Wolfgang Maass, and all of that is very, very interesting indeed.
Yeah, and you also in Switzerland you have Oh, I'm blanking on the name. Sorry, I'll find it again.
Just to a reminder of the attendees, if any of the attendees want to participate, please let me know. Raise their hands. I will open their mics. So yes, the idea is to have an open discussion so anyone from the community can participate on it. So okay, let's go. There is allowed to talk. So Elvin wants to talk. Please, Elvin, I believe you can speak now.
Hi, do you
Hello.
hear me?
Yes.
Hi. It's Elvin here. I want to quickly I also mentioned in the chat, but I also want to quickly mention here that there are also neuromorphic continual learning works that basically look at somehow intersection of computational neuroscience, but with the standard AI, basically trying to apply brain-inspired computing towards continual learning. It's basically based on neuromorphic learning, so neuromorphic chips and everything. Our lab is also one of the labs that works in that direction. So I don't know if anyone else is here aware of those things. That, for example, IBM, Intel,
you have
some
like a
people
lot of chips
at
now,
Zurich.
right? Yeah,
Sorry?
low heat too. You have quite a fair bit of chips now that can do that. Low heat 2 is one that comes to mind. IBM has its own. There's definitely some biologically inspired things in those chips. There also are things that are not really biologically plausible. I'm thinking graded spikes, for example. But they do have the usefulness in an engineering setting, right? You can do things in engineering and in artificial networks or artificial hardware that the brain cannot do, and that's a good thing, right? You can come up with solution that the brain has come up with in the biological setting. Your solution in an artificial setting could be better in some specific context with some specific task with some specific output in mind.
I mean, I specifically work on low heat 2 for continual learning, and one of our ideas, as Professor Christopher Kahn mentioned, like one of the application lines is this on-device learning, where you need you have the constraints and where you need more maybe energy efficient and compute efficient learning. I think there, like a neuromorphic computing learning type of approaches could be very valuable. But of course, combining.
Okay, so let's go to the next question from Marty as well. So is there any use of the concept of both short-term and long-term learning in the current work in continual learning? Or we have been discussing on this idea of how can we apply these two concepts coming from neuroscience to the continual learning approaches.
Can I answer maybe on one thing related to that question? I would say that, for example, short-term memory is definitely a way of could be seen like as a memory buffer in this replay methods, and basically once you replay from short-term to long-term memory, that's the consolidation of knowledge from for long-term. So I think that's sort of I would say the direct relationship there.
It's a good question. I actually haven't really thought about having a one-on-one mapping. I think it's very hard to do. The details in the biological implementation of long-term memory and short-term memory that you don't find in artificial neural networks. For example, in short-term memory, when you're speaking about biology, you are going to use elements of the neuron that are already there to help strengthen some connections for a very short amount of time. And that is basically what we call short-term memory. For long-term memory, you're going to do something completely different. It starts with the short-term memory, but then you are also inducing the creation of new proteins and changes in structural morphology of the neurons and all of that, which I don't think there's a direct analogy in conditional learning, at least at the moment.
Christian, do you want to add something?
No, not really. I was wondering if this question related also to some extent to episodic RL, right? So this idea that when you're in this novel state, right, you can sort of compare how similar is a given state to a previous state that you can then use to solve the current task at hand, right? So maybe I would advise to have a look at that literature as well, right? Episodic RL.
So we're near to the finish of this section. So now I have a question the other way around. So we have been talking about how can new-inspired neuroscience can be very helpful for continual learning, and multiple methods taken from it, we can apply it to continual learning. Do you think that we can go the other way around? Can continual learning be useful for the neuroscience community? Maybe to run more experiments, maybe to understand new things. What is your opinion on that?
So, yeah, I mean, just generally speaking, right? So I always think there's like a good synergy between AI and neuroscience, right? And maybe to some extent the sort of the field of computational neuroscience is sitting in the middle of both, right? To some extent, I wouldn't say it's exactly that, but yeah, I mean, this concept, like even for instance in the network that I was presenting, right? So this is not purely AI as people would like talk about it, right? But at least modeling the dynamics obviously get us, to some extent somewhere, and allows it to understand a bit more the systems, right? And maybe there's some representations that emerge that allow us to even make sense of what's already at stake in AI, right? And or even emergent properties of AI systems that allow it to understand also the brain. That's like, I mean, that's just in general, right, the case. I think obviously there's a nice synergy between both worlds, and it should be amplified, in my opinion. Yeah, for sure. I don't have an example, really, like a true concrete example that I can give you. Usually, if you look at it, it's mostly from the neuroscience towards the AI side, right? Like I don't know, deep reinforcement learning, the convolutional neural networks, and so forth. But I mean, at the same time, so you can use, for instance, it's been a while already, but convolutional neural networks also allow us to make sense of the brain, right, to some extent. So obviously it has been inspired by the brain, but it also can then retrospectively also be used to understand some specific representations.
Yeah, I think there's definitely a lot of potential for synergistic approach between artificial networks and biological networks understanding. For me, it's always a loop, right? So you come from one, go to the other, back to the first. Why? It's because, let's say I have some experimental data from biology and I build a model on that. That model is going to allow me to not only test if using the data of biology if my model is accurate, but that model, if accurate, will allow me to make predictions that I can then test in biology. So that's the loop that I think has a lot of potential. Now, in terms of applications of that loop, I think we're still in the infancy of its use, just because it either asks for people with a lot of knowledge in both fields, or it asks for a lot of collaborations from people from both fields that don't necessarily understand the field of the other, which can make things tricky. But overall, I would say there's a lot to learn from neuroscience to AI and from AI to neuroscience. From a neuroscience point of view, testing in models is definitely helpful to, reduce the number of animals that are used in experiments, to test hypotheses that you could not test in biology. There's some things that you just can't do in biology that you could do in models. And then from the model prediction, you could infer how the biology works. And from an ML AI perspective, I think, we're building now these huge models, these huge LLM models that are completely black box. Well, it's a problem to know how they work. And biology has been developing tools and methods, statistical analysis, dimensionality reduction techniques, all of those for decades that can then be used to understand what those models are doing, to probe those models in the same way, right? So I think we're still in the infancy of that back and forth, and there's a lot of benefit that we can find in using all the knowledge of both fields.
Great. Thanks, both of you. Sadly, we need to go on with the next section, but I will thank Jeremy, Christian, both for participating in this open discussion. I mean, I have a lot of fun asking difficult questions. I learned a lot about it, so thanks both of you. Also, thanks Elvin and all of the attendees that are listening for participating as well.
Cool. Thank you, Julio.
Yeah, thanks a lot.
So